everyone, my name is Venantius and I'm here today to present about Monte Carlo simulation of public transport delays to answer the question, how likely is a public transport trip to be delayed by more than 10 or 20 minutes under different travel conditions? So you can see why public transport punctuality is important, and here's an explanation of my presentation, what am I testing statistically, and I took my dataset from Kaggle, which contains 2000 records and 24 columns. So first of all, you want to upload your content from Google Drive or your dataset from Google Drive. Next, we're going to do some setup using Panda that helps us manage and clean data in tables, and NumPy, which provides mathematical and random number tools for simulations. Now I'm loading the dataset. So this dataset contains over 2,000 records of public transport trips, including columns like delay times, weather, and traffic congestion. The pd.read_csv function reads the CSV file and stores it in a Panda data frame named df. So now what I'm doing is I'm changing labels for the weather. For instance, light rain to rain, rain or shower to rain, rainy to rain, and then sunny to clear, and clear sky to clear, just to make it more simple and to make it more brief. Okay, so next what I'm gonna do is I'm going to parse date or time and create a single timestamp. This section combines separate date and time columns into one complete timestamp. By converting both columns into standardized date-time format, we make it easier to analyze time-based trends like peak hours or seasonal effects. The errors in equals to coerce argument ensure that any invalid or missing values are automatically converted into NAT, or not a time, instead of crashing the program. Finally, combining date and time strings creates a single column timestamp, which represents the exact moment of each trip. This unified time variable and is important for later analysis or visualization. So now what I'm doing is I'm ensuring numeric types. Here we ensure that all quantitative columns are stored as numeric data types like integers or floats rather than text. This step prevents calculation errors during statistical analysis or simulations. Since text-based values like NA or unknown cannot be used in formulas, the pd.to_numeric function safely converts each column to numbers and replaces invalid entries with NaN, missing values. Doing this early guarantees that later mathematical operations such as averages, quantiles, and random samplings will run smoothly and correctly. It is a crucial data validation step before modeling. You can see that process now. So now I'm standardizing categories. This section cleans up all categories text columns by converting them into consistent lowercase strings and removing extra spaces. Real-world datasets often contain messy variations like rain, or rain, which technically look different to Python. Standardizing them into lowercase and stripping spaces ensures that filters and comparisons work properly. The replace function also substitutes text like nan or none with a common non-label, making missing categories explicit and easy to handle. This creates a uniform, cleaner dataset that improves accuracy and grouping and filtering operations. So what I'm doing now is I'm creating a helper feature. We create two new binary variables to simplify our analysis later. Is_peak marks whether a trip occurred during peak hours with 1 for yes and 0 for no. And is_holiday checks if the trip happened on a public holiday, again assigning 1 or 0 accordingly. Next, I'm targeting a variable. Here we define our main outcome variable, the arrival delay in minutes, which we will simulate and analyze throughout the project. We simply copy the original delay column to a cleaner, shorter name so it's easier to reference later in the code. Now I am handling impossible values and outliers. This step removes extreme outliers and usually high delay values that can distort our result. We calculate the 99.5th percentile, meaning the top 0.5% of longest delays, and set it as our upper limit. Now what I'm doing is drop rows with critical nulls. So we remove rows missing key information required for simulation and analysis. Without valid delay, weather, or traffic data, we can't accurately estimate probabilities or correlations. The drop none method safely eliminates incomplete records only in these essential columns, keeping the dataset reliable while retaining as many usable rows as possible. Okay, so that's the result. And now I'm gonna do a quick check. This quick check ensures our dataset is clean and suitable for simulation. So just hang on a minute. So the output there shows how many records exist for each weather and peak hour combination. It confirms that both condition rain peak and clear off peak have sufficient and reasonably balanced sample sizes. Okay, so for this part, I'm going to speed up everything because it's gonna take a long time. So basically what I'm doing now is I am subsetting function for scenarios. But this code filters the dataset to extract only the records matching specific conditions such as rainy peak hours. It ensures the Monte Carlo simulation uses relevant, realistic subsets of data. Without filtering, random sampling would mix unrelated scenarios, producing inaccurate probability estimates for each simulation. So if you're wondering, the RNG function above is the random number generator, which essentially produce consistent, repeatable random samples essential for reliable Monte Carlo simulations. So now we're in the Monte Carlo simulation function. This is the heart of our project. We perform a Monte Carlo simulation by randomly resampling 20,000 values from historical delayed data. The replace equals to true means every draw is independent. The same trip might be selected multiple times, mimicking random variability in real-world events. Okay, so now I'm creating the scenario, which rainy peak hour is the best scenario and rain peak hours is the worst case scenario and clear off peak is the best case scenario. And we're running the simulation. Okay, so I'm actually having some trouble here, which I am just going to skip. It's actually just a minor problem, no big deal. So basically we simulate 20,000 random delay outcomes for each scenario. Now you can see the result there. This code filters data into two groups, rainy peak hour trips and clear off peak trips. It finds 104 and 253 records respectively. The 20,000 confirms both simulations successfully generated 20,000 random samples each, modeling thousands of possible delay outcomes per scenario. And this is the summary, which you can see. You can pause it if you want. I'm afraid I don't have time to go through it one by one, but that's the mean, median, the probability, 95th percentile. And now what I'm going to do is I am going to create a histogram and CDF function and a comparison bar chart to visualize the data, which that's the function I'm using. Why am I using CDF or cumulative distribution function? Because it shows the probability that delay x, the curve rising toward 1 lets us read the exact probabilities at any delay threshold. So in a few seconds you can see the graph, which you can pause it. I'm afraid I don't have enough time to go through it one by one. There it is. That's the graphs. We have 5 graphs. And finally, what I am about to do is calculating the probability of delays exceeding 10 and 20 minutes. This code uses NumPy to calculate the probability that simulated delays exceed 10 and 20 minutes for both scenarios. So the result, it quantifies risk levels directly from the Monte Carlo result. Rain plus peak delays exceed 10 minutes, which is 64%, while clear off peak is 62%. There's about 64% chance of being 10 minutes late in rainy peak hours versus 62% in clear off peak. Now, for the second one, I am filtering and comparing scenarios for Monte Carlo simulation. Rain plus peak versus clear plus off peak. So that's the code that I'm doing. I'm just going to jump straight to the result. The result shows that rain peak trips are fewer but slightly more variable, indicating heavier, less predictable delays compared to steadier, more consistent off-peak travel. That is it. I apologize if I am not being clear on this presentation, but I hope you guys get the picture, and thank you.